Welcome back, everybody. Here we are in Unit 1, video number 2. Today we're talking about measures of central tendency and measures of spread. Measures of central tendency are probably things that you've all seen before. We're just measuring the approximate middle of our data. You've all heard of the mean, median, and likely the mode as well. But for completeness, we need to cover these topics. So here we go. The arithmetic mean is what you've all called the average your whole life. In statistics, we tend to use the word average as more of a general term for any measure of middle. We'll try to be more specific and say the mean when we mean mean, but sometimes I will slip up as well and use the word average to mean mean. In the last lecture, we were talking about samples versus populations. We'll have two different formulas. One formula when we're dealing with samples, and another formula when we're dealing with populations. We said in the last one that sample formulas will tend to have our standard English letters, and then population values or parameters will have Greek letters. For the arithmetic mean, we just sum up all of our values and divide by the total number that we have. So in the sample case, we have x bar is the sum of all the x's divided by lowercase n will be the size of our sample. For populations, it's the same formula, just different symbols. We'll use the Greek letter m or mu for the mean, and then we'll sum up all the x's and divide by the population size. And we'll denote population size with uppercase N. Moving on to the median. The median is simply the middle score of a data set. The symbols for this one aren't as standardized. Sometimes for sample medians, we use X with a tilde above it. But most times I see median as a written out rather than as a symbol. To find the middle of a data set, you need to sort your values. After you do that, if you have an odd number, it's pretty easy to locate where the middle is. When you have an odd number or an even number of data points, then the middle isn't quite as clear, like in this example. What we'll do is we'll take the mean of the middle 2 whenever there's an even number in your set. So in this case, if this is sample data, the median would be the mean of the middle 2, which is 30 plus 70 over 2, which is 50. I don't know what the units are for these examples, but I'm going to write units just so I remember that I should always write units when I'm calculating these sample statistics. The next measure of middle is the mode. This is the most frequently occurring value in a data set. I don't see this used that often when we have actual data that's measured. Sometimes it might be used when we have something that's categorical. For example, if I wanted to know the average, shoe color of the students in my class, I might count how many people have black shoes, how many people have brown shoes, how many people have blue shoes, and say black was the most. Then the mode is black. And then I would say that that's the average shoe color. Each of these measures of middle has an advantage and disadvantage, and their advantage is often their disadvantage. I found this little chart somewhere. Most of the time we're going to use the mean to measure average. Its advantages, it takes all of the data into account. Its disadvantages, it takes all of the data into account. which means that if there's an unusual score, the mean will be affected by, say, one strange value. Whereas, in contrast, the median has an advantage of it doesn't take every score into account, but it has a disadvantage of it doesn't take every score into account. The nice thing about the median, however, is because it doesn't take every score into account, it's a good choice when you do have, a few extreme scores. And then the mode, I think, is good when we have something that's non-numeric. But otherwise, it's not that great because oftentimes there isn't even a mode. If I have a bunch of values that are all unique, then there is no most frequently occurring value in my set. Last time we were looking at histograms and we were looking at the shapes, and we saw the classic, bell curve, which is sort of a, we could call that a symmetric shape where you can draw a line through the center and, the curve is the same on each side. Now, we didn't see examples of data that was skewed to the right or skewed to the left. Those are often very commonly occurring shapes. When we're talking about these shapes, we bring up the term mode again, and the mode is sort of, when we were making a histogram, remember we had different classes, and each class had a certain frequency, and the class with the most items in it is then the mode in this case. So we use the mode in a slightly different way when we're talking about histograms, or in this case, I sort of smoothed out the curves to have more of a continuous case here. But in the case where, say, we're looking at this left skewed graph, the mode is where the peak is. In this situation, the mean and the median would appear likely to the left of that mode because you'd have values that are below that are bringing down, particularly the mean. When you have something that's symmetric, the mean, median, and mode tend to be roughly the same. When you have something that's skewed to the right, you have your mode at the peak, and then your median and mean tend to be to the right of it. Now, memorizing this sort of idea, or having a clear concept of this used to be more important back in the day before when it was difficult to make plots. But now we make histograms so easily that it's unlikely you'd ever just calculate the mean, median, and mode and then make some decision about what sort of shape you have without actually plotting it and seeing the shape. But it is gives you some sort of reference. It's some way to give you a rough idea what your plot might look like if you haven't had time to plot yet. There's a little exaggerated example here to discuss, sort of the advantages and disadvantages of, which measure of central tendency you should use. So we have this example where we have a little company and they have 4 graduates from BCIT and they each earn a measly $24,000 per year. The owner of the same company makes $114,000 a year. The company then puts an ad in the newspaper or online and says, hey, come work for us. The average salary is $42,000 per year. Is this deceptive? Possibly. Let's calculate the actual mean salary of these 5 employees I guess it's 4 employees and the owner. So we have 5 people. It's the entire company. So because it's the entire company, I think we can view this as a population. So I'm going to use my population parameter mu. I'm going to sum up each of the salaries and then divide by however many there are. So it's employee number 1 is 24,000, and then the next person is 24,000, and 24,000, and 24,000, and then the boss, who makes 114,000. Divide that by the 5 employees that they have, and it comes out to be 42,000. So in their ad or job posting, they haven't really lied. The mean salary is 42,000. However, no one makes that amount of money. It's not even close to what the person who's going to get hired will make. So this is a situation where we might choose to report the median instead, which is just the middle score. And when I wrote this out, luckily I listed them in order. I guess there are 5 employees, so finding the middle shouldn't be too hard. It's just 24,000. Now that is a much better representation of what someone might make at that company. They could even report the mode in this example, because the most frequently occurring salary was 24,000. So there's a sort of an exaggerated example of, there's an exaggerated example of why we might choose the mode or median over the mean. You often see this with things like property prices. Instead of listing the mean property price for a home in Vancouver, they'll list the median, because it won't take into account necessarily, some large mansion that might bring up property values. In my neighborhood, somebody just bulldozed one of the houses, or actually 2 of the houses, and put up a giant house. Now, that house is going to be worth a lot more than all the houses around it. So the average price in my neighborhood, as demonstrated by the mean, would be higher than what a typical house is worth. So therefore, the median is a better choice. I'm not saying that the median is always a better choice. There are just sometimes where that might be appropriate, particularly when you have, a few extreme values that is messing with what is a typical data point. A second ago, my screen flickered. I must have hit last year's gradebook, and I opened that for a reason this morning, so that I could show you sort of different distributions, I guess. We're so used to seeing, always seeing bell curves and things that are skewed to the right, but is all data always like that? Not always. Here's an example of last year's first midterm. Last year they had 2 midterms. You'll see that the shape of this thing, I wouldn't necessarily classify it as, skewed right or left. It is probably somewhat symmetric. It's not very bell-shaped. You can see that they did quite well. You can see that when I grouped the data together, that the histogram for the whole group was pretty similar in shape to either set. When you have small data sets, like in this case, class sizes were only 18 and 16, it's hard to get a good idea of what the population is going to look like based on just, say, even one set. You can see last year the means on the midterm overall was 77, which is pretty good. The median was 76, also pretty good. Again, an indication that my data is pretty symmetric, which is represented in this plot. I made a plot here comparing set A and set B just by their mean, and it looks like set B did, like 3 to 4 times better than set A, when actually it was only a 2% difference between these two plots. So I was definitely deceptive there by messing around with this scale and starting the scale at 75% rather than starting at, say, 0. So that's one example of different shapes. And most of you probably right now are interested in, how did they do last year to see how hard this course is. On the second exam, the results were a little, more diverse here. We had some people doing really well, and then some people doing not so well. On the first midterm, I don't think we had anyone fail. And on the second one, we had 7 fail, but it was balanced out by 9 people got over 90%. So it was one of those situations where they sort of knew it or they didn't know it. The average turned out to be sort of your very typical 65. The median is pretty nice, 64. No bell curve there. Kind of an ugly looking curve, really. If we looked at set A versus set B really had a situation of they either really knew it or they just sort of knew it. And then set A was just a pretty uniform distribution there, which is kind of interesting. This time set B won out. I can't remember, it was on exam 1, was it also set B? Let's take a look. Oh yeah, set B were the superstars of last year. Now I'm almost afraid to show you what happened on the final exam. The final exam plots are very striking. We could say that they're skewed to the right as they sort of tail off in this towards the right direction. It's kind of scary to not see anyone in the 80s or 90s. The average wasn't super great, 53. We'll talk about the median instead because it was 55, which is a bit better. In this case, I believe our final exam occurred on the same day as the thermodynamics exam, and most people had already had a pretty good grade in this course, and they sort of, I hope that it's the poor results on the final were due to the fact that they had to study for thermodynamics and not for, they knew that they were already sitting okay in this course. But it gives me an opportunity to talk to you guys about skew. Definitely skewed to the right in this situation. Looking at their final grades, even though they had a pretty terrible final, overall, everything balanced out nicely. Their final grade ended up being a pretty decent bell curve. You can see that here in the first plot. The average for the course, I guess I have a little glitch in my spreadsheet there, but it looks like it's in the high 60s. Oh, there it is. It's 68. The median was also 68. Again, set B1. Set B's overall grade also followed a bell curve. Set A's not perfect, but not bad. We'll discuss this box and whisker plot as we move along. We'll also discuss some of these other statistics, particularly the standard deviation, as we move along in the lecture. But I just thought this was kind of fun to take a peek at some real data rather than just talking about this made-up company. When we were talking about this skew, going back a second, it always seems backwards to me that the direction of the skew, in this example where we have skewed to the right, all my data is over on the left side, yet we say it's skewed to the right. So I guess say that this little tail here points the way. So if the tail is pointing to the right, then it's skewed to the right. If the tail is pointing to the left, then it's skewed to the left. Another thing that maybe we should add here is maybe what happens if you have more than one peak. Sometimes you have data, like one of the classes exams had something like this, where they had a lot of people doing not so great and a lot of people doing really great, but nobody really in the middle. That's a bimodal distribution. Or we could have, multiple peaks, trimodal or multimodal distribution. So just to get the, terminology of saying mode also corresponds with the peaks of your histograms and continuous plots. I think we can move on to another example then. I have some data here where we're looking at 2x4s. We want to decide, should we get our 2x4s from supplier A, they have great names, or supplier B? And the two companies are pretty much equal in terms of reputation and price. So we're going to try to figure out where to get them from based solely on quality of the boards that they have. So we asked them one day, hey, company A, company B, send me 50 boards. So that day, you inspect all 50 boards from company A, and you find that there were 17 defects. Then you look at company B's 50 boards, and you find 21 defects. Now, we're going to be very particular about our defects. I think boards can have more than one defect. It could have a knot and a twist and be too short, and another one could be too long and have a crack. So you can have more than 50 problems in 50 boards, for example. So we did this each for 20 different days or 20 different shipments. We said, hey, send us 50 boards. And we studied each company. So on day 14, we got 50 boards from supplier A and found 31 problems. And from supplier B, 50 boards had 41 problems. Just looking at the raw numbers, it's kind of hard to tell which one is better. On day 8, it looks like supplier B is better. Remember, smaller will be better in this example. On day 14, supplier A is better. So in general, which one would we prefer? Last time we made a stem and leaf plot. This time I made what's called a back-to-back stem and leaf plot. I noticed that the values varied from the teens to the 70s. So I made my stems 1 through 7, 10, 20, 30, 40, 50, 60, 70. And then I populated supplier A and supplier B. I even sort of sorted them as I put them into their respective supplier. So, for example, this number 79 here is represented by the 9 here. Or the number 38 here is represented by this 8 here. So I just went through and did it for both companies. It only took a minute, and it gave me a pretty good idea of who the winner is, actually, even without doing any more. I can see that we have sort of a classic bell curve for supplier A. Supplier B might have a bit of a skew, and in this case it would be a skew to the right, or a skew towards the higher numbers. Now in this case, we're looking for which one has lower defects. So if I had to pick one of these just by looking at the pictures, I think I'd go with supplier B, because I see that most of their defects are in the 30s and 40s, whereas supplier A maybe has too many defects in the 40s and 50s. So with just a quick analysis, I've pretty much, I probably have made the correct decision. We'll go ahead and we'll calculate the other stats for this just to see what they say, but I'm pretty sure at the end, we're going to say we like supplier B. So I made a little chart. I decided to calculate the mean, median, mode for both companies. In order to get the mean, I needed to add up the total number of defects for each one. And that is a stat in itself. The total number of defects for A was 927. The total number of defects for B was 862. And we had studied 50 boards a day for 20 different days, so we had 1,000 boards from each company in total. So there were 862 defects in total out of 1,000 boards for supplier B, for example. And right there, that tells a pretty good story. So don't overlook some of the most basic values, trying to come up with more complicated statistics. But moving on to the mean and the median, calculating those, maybe I'll go back and look at the data here. As soon as I get my pen to work. Going back to the data, this is clearly sample data, so I think I would be using sample statistics. I'm going to use X bar, and if I'm calculating the mean of supplier A, for example, I would add up all the values in A and divide by however many there are. In this case, we had a total of 927 defects when we added this column. And then we divide by the total number of samples that we had, which were 20. And we come up with a total, or a mean, of 46.3. For units, I guess it's defects in 50 boards. We could do the same thing for supplier B. Supplier B had a total of 862 defects. So that will be 862 over 20, which ends up giving us a value of 43.1 defects in 50 boards. Repeat the units there. So we can see that the mean of set B is lower than the mean of supplier A. For the median, we looked at the middle value. The middle value is hard to find in the original data set because the values aren't sorted. So we need to sort these values. Luckily, when I wrote out these stem and leaf plots, I listed the values in order so we can find the middle pretty easily. In this case, we have 20 values for each set, which is an even number. So we want to find the mean of the middle two. So we're going to look between the 10th and the 11th value. So the median for supplier A, I'm going to just start counting and I'm going to find it between the 10th and 11th value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So it's between these two values. Be careful, don't just take the mean of 7 and 8. Remember, there's also the stem of 40. So it's 47 plus 48. And we're looking at two values. So we get 47.5. Again, the units are defects in 50 boards. And we can do the same for B. Just count until you hit the 10th and 11th value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That's these two values. So 41 and 42. The middle one is 41.5. Defects of 50 boards. So in all categories, B is the winner. We knew it just by looking at our plot. Sometimes it's not as obvious, though. And we do need to do this further analysis. We can calculate the mode too, the mode of A. That's the most frequently occurring value in supplier A. Sadly, it looks like it's a tie. There are two 22s, two 47s, and two 61s. So is it 22? Is it 47? Or is it 61? For supplier B, I think there was only one where we had a repetition, and it was 45. So again, the units are defects in 50 boards. Make sure you include units with all of your values. Also, maybe this is a good time to talk about sig figs a little bit. My data is all given to, no decimal places. I have 2 sig figs. And then in my means, you'll notice that I said 46.3 and 43.1. I actually went one decimal. I added precision to those values. And sometimes this might seem wrong to do, or, you've kind of been trained that that's wrong to do. But sometimes it adds information. In this case, maybe it wouldn't add much. I think I should maybe be better off to round these and say 46 and 43. But in other instances, I find sometimes by having the decimal place, it brings additional information to the reader. As long as the reader knows that it's, the data isn't more precise than they might be led to assume by that. We'll do another little example shortly where I think it's better to have to break the rules on precision and accuracy just to convey more information. We'll see that in a little bit. So here's the same results we just calculated, and I made nicer histograms for the two suppliers. You'll see that these two histograms look exactly like the stem and leaf plots, actually, because I made the categories the same. I went, groups of 10, 10, 20, 30, 40, 50, 60, 70. When I made these two histograms, you'll notice that I made sure I made the categories the same because I'm trying to compare the two groups. You'll notice that I kept my scale on both, 0 to 7, so that I'm not deceiving as I'm trying to compare the two. You'll notice that I put nice units on my x-axis. You'll notice that I have terrible titles. These titles should say more. When someone looks at these two plots, they should be able to have some idea of what happened here or what this data is about. So these titles should definitely be beefed up to say something about what this data is. 2x4s collected on 20 different days from two companies, or just more detail to help the reader if they jumped straight to this plot first before looking at anything else, which often readers do. So those are our measures of central tendency, at least the main ones. We'll move on to measures of variation. How spread out is our data? Most of us are familiar with the term range. That's just the maximum minus the minimum value. In English, it is often from A to B is a range. In statistics, it's an actual number where we calculate the difference between the max and the min. It's super easy to calculate. However, it is very susceptible to outliers. Again, with the example of all the houses in, a certain neighborhood, say you have a little cul-de-sac where there are 9 houses that are all $1 million each, but then right at the end of the cul-de-sac, there's a giant mansion that's, worth $13 million. If I calculate the range, it'd be 13 minus 1, which is a $12 million difference, or a very large range, indicating that the houses in that group are very inconsistent. However, most of the houses are very consistent. They were all $1 million, and that got missed by the range. The standard deviation tries to take into account all of the values, but it will also be affected by that large mansion at the end of the street. At least it will be hidden a little bit by the fact that there were 9 $1 million houses to kind of off balance it. The standard deviation is a term most of us have heard, maybe even calculated. For this one, we have our sample version, S, and our population version, sigma, Greek lowercase s. The formula is interesting because it has a lowercase Greek s and an uppercase Greek x. Sorry, lowercase Greek s and an uppercase Greek s, sigmas. These formulas are a bit of a slog to calculate by hand because, well, you have to find the difference between every value in your data set and the mean of the data set and square all of those things and then divide. So basically, standard deviation is sort of an average distance of each point away from the mean. I used to ask that as a test question. In your own words, describe standard deviation. And I always felt bad about it because I didn't want the answer to be their own words. I wanted them to be my words. I wanted them to say it's the average distance of all of the points in a data set from their mean. But I would get all kinds of crazy answers, and then it would be hard for me to justify that something was wrong when I said, write your answer in your own words. You'll notice that for this example, the formulas aren't exactly the same. They're different not only in symbol, but their formulas are slightly different. The sample version is biased a little bit. We divide by 1 less than the sample size. This biases the number. It has the effect of making the standard deviation slightly larger than it might actually be. Now, it only has a big impact on small data sets. But when you have large data sets, if I have 1 million values and I divide by 1 million or I divide by 999,999, it won't make much difference. But this is to help us when we're dealing with particular small sample situations. Generally, we're using statistics to estimate parameters. And if we're going to be off one way or the other, this is almost like a safety factor here. We're going to err on the high side. And to err on the high side, we'll just adjust the sample value by dividing by, a little bit less. And that will inflate the overall value. We would rather err on the high side when talking about standard deviation. And we'll see why this is as we use the standard deviation as we go along. So now it becomes important that you know whether you're dealing with a sample or a population, because in this case, it's going to matter which formula you choose. My house has 5 kids. They're aged 1, 2, 3, 5, and 9. and I want to find the average or mean and standard deviation for my kids' ages. I guess I should study how old my own kids are. Since I'm not planning on having any more than 5, I think this is a reasonable situation for me to consider this a population. So if I'm going to calculate the mean of my 5 children, I'll just add up all their ages and divide by however many I have. And in this case, my children are a nice age because it makes this calculation pretty easy to do without a calculator. It looks like the average age of my children is 4 years. I plotted this on the number line here, 1-year-old, 2-year-old, 3-year-old, 4-year-old, and 9-year-old. And then I put a dotted line here to represent the mean. What is the standard deviation? Well, that's just the distance of each kid from this dotted line. So the 1-year-old is this far away from the line. The 2-year-old is this far. The 3-year-old is 1 unit away. The 5-year-old is 1 unit above. And the 9-year-old is 5 units above. On average, how far is a kid of mine away from the mean? That's what standard deviation is. It's the average distance away from the line. So distance away from the line is just the value, any particular value minus the mean. That's the distance away, the distance between each kid and the mean. I want to add all those up. I want to add all those distances up and then divide by however many kids I have or how many distances there are. That's standard deviation, roughly. Now, what happens here, if I use this formula as I just wrote it, I end up with a problem is that some of my kids are above the mean and some of my kids are below the mean. So when I do this summation, I'm going to have positive and negative numbers and they'll all cancel out. And this will end up having a total of 0. So to fix that, I could either use absolute value bars around these differences, like a vector magnitude, or in stats, we've decided to fix the problem by looking at the squared distances, and then at the end of it all, taking the square root. Now you'll notice that I kind of overfixed it because I put the n under the square root as well. So this isn't the mean distance of all the points from the mean. This is just an average. It's one way of doing it. In this case, we can do this calculation by hand. It's not too bad. Kid number 1 is 1 year old. The mean is 4, and we'll square it. And then we'll just do that for all of the children. I have a 2-year-old, a 3-year-old, a 5-year-old, and a 9-year-old. Divide that by however many I have, and then take the square root. Again, take out your trusty calculator, or soon we will learn, a shortcut. Your calculator has a built-in mode that will solve this for us, so we don't have to do quite as much work. Let's see. I guess I'll just do it. 9 plus 4 plus 1 plus 1 plus 25 all over 5. So that's the square root of 40 over 5, which is the square root of 8, which is, I don't know, I think it's 2.8. So the average distance any one of my kids is away from the mean is roughly 3 years. In this case, I think it's better to say 2.8 years. When you hear about things like, how many children does the average Canadian household have? And they'll generally report this as a number like 1.6. Each Canadian family has on average 1.6 children. If we round that to 2, we sort of lose some information. I think seeing it as 1.6 is better. And in this case, it might be good for me to leave the 2.8 years rather than rounding it, even if it does seem a little deceptive. By the way, I do not have 5 children. This was just an example that had nice numbers and it was nice and visual. I thought maybe we could crack open our calculators. You all have the Sharp calculator. In order to do statistics, there's a mode, and mode number 1 is stat. And then once you choose that, there's different stat modes. For this one, we want SD. It doesn't stand for standard deviation. It means single data set. So we have one data set here. So I'm going to choose mode 0. Now my calculator is in stat mode, and I can enter my 5 kids. To do so, I type the first kid, who is 1, and then I press the data button. And now my first kid is in there. And then I enter the second kid, who was 2 years old, and I hit data. And then the third kid, which was 3 years old, and I hit data. And then my next kid was 5 years old, and I hit data. And then my next kid was 9 years old, and I hit this data button here. Now I have my 5 children in there. If you look above the buttons on your calculator, you will see above the button number 4 is a green symbol for X bar. That's your mean button. To get to these green things, you use your alpha button. So press alpha and then 4 and then equal, and it will give you the mean. The standard deviation button, this is the one we really want to know, is above the button number 5 when it's a sample. So if I do alpha 5, I'm calculating S, or the sample standard deviation. You'll notice that it doesn't match the value we had of 2.8 years. The sample value is 3.16. But in our example, this was a population, which is rare. Almost everything we do in the course will involve sample situations. So no alpha 5, because that's maybe the most important standard deviation button you have. The population standard deviation button is alpha 6, and it shows sigma of my x variable. I hit equal, and there we go. We get our 2.8 that we had calculated by hand. So in one of your labs, there's a tutorial on this. So if you missed something, and it's kind of hard to see when my cursor is hovering above these buttons, but I just wanted to give you an idea of how to do these things. So you don't really actually have to do standard deviation by hand, because it's really tedious when you have larger data sets in particular. In the example that we had chosen supplier B, and supplier B was the one that had the lower mean. To calculate its standard deviation, I took its mean. Remember, it was 43.1. And I had to subtract that value from each value in my data set. So this first term here is 21 minus 43.1. And I had to do that for every single one in the list. You can see even with 20 values, it becomes pretty tedious. After getting all those, I then had to square them all. So this value here is 21 minus 43.1 squared. We have to do that 20 different times. Of course, you can tell that I cheated here. This is an Excel plot. I typed a formula into the first two cells, and then I just filled it down and calculated all the rest. We need to find the sample standard deviation for this one, which is S. The formula given like this. I've already calculated the numerator of this formula then. It's the sum of all those squared differences of 3569.8. And then I divide that by however many values there were there. We had 20. And remember, when it's a sample, we adjust it ever so slightly by subtracting 1. And we end up with a standard deviation of 13.7 defects in 50 boards. Now, we've calculated standard deviation here. We calculated the standard deviation of my family. Are these, big numbers, small numbers, good numbers, bad numbers? We need to start thinking about, what does standard deviation actually mean? The average distance away from the mean. It is often desirable to have small standard deviations so that you can predict things better. The less variation you have in your data, the easier it is to predict what a likely outcome will be. If your standard deviation is very small, then if I'm going to make a guess at a value in the data set, I would definitely pick a value, either the mean or very close to the mean. But if I have a very large standard deviation, if I take a random draw from a value in the data set, I really have no idea what I'm going to get. So small standard deviations are desirable. Now, small is all relative. It's relative to the size of the mean. In this case, 13.7 is rather large compared to a mean of 43. Had this been a value of 0.137, that would be very small relative to a value of 43. And had this number been 137, that would be very, very large relative to 43. So you never talk about the standard deviation by itself because it's meaningless. You have to always talk about it in conjunction with its mean, because otherwise you have no idea if it's large or small. So if you're ever writing a little report and summarizing data, make sure you talk about the mean first and then talk about the standard deviation. Don't get all carried away and start saying the standard deviation of one thing is better than the standard deviation of the other without first having talked about the mean, and also talk about what it means to be better. I'm trying to think of situations where you would want maybe a large standard deviation, and it's really hard for me to think of one of those on the fly, actually. I wish I hadn't just said that out loud. Maybe a situation in genetics where you want things to be diverse, to improve the health of a population. You want genetic diversity. In that sort of situation, maybe you'd want it'd be desirable to have large standard deviation over small standard deviation. Yeah, I don't know. There might be other examples, but that's the best I can come up with on the fly. I feel like I kind of recovered pretty well in that one. There are other measures of variation besides the range and standard deviation. A more theoretical one than the standard deviation is the variance. It is basically the standard deviation. It's just the standard deviation squared. We use this in theoretical statistics all the time, but we don't use the variance that often in many applied or practical situations. So variance is something I think we should, I want to have that in your vocabulary, but I don't think we'll use it that much, primarily because it messes with the units. You end up with squared units, which in the example that we're doing with defects per 50 boards, it'd be really awkward to have to say defects per 50 boards squared. There's a terrible little note here about the variance when talking about money and square dollars. I kind of failed at making my loony square there. I mentioned that we should never talk about the standard or the mean without talking about this. Let me try that again. I mentioned earlier we should never talk about the standard deviation without talking about the mean. So why not create a statistic that just uses both? The coefficient of variation does just that. It's the ratio. We take our standard deviation and divide it by the mean. Two formulas there, one when it's a sample and one when it's a population. Oftentimes it's multiplied by 100 so that we can list it as a percent. The coefficient of variation is really nice. I don't see it as commonly used. It's in every stats textbook, but I don't see it, written in a lot of papers. It's certainly not something you'd see on the news or, on TV. But it is a really nice statistic, particularly when you're comparing multiple things or two things. Its first nice property about it is because it's a ratio, we lose the dimensions. So there are no units. I mean, multiplying it by 100 gives us it as a percentage, but this allows us to compare, anything. If I want to know the amount of variation in the midterm grade of our course to the amount of variability of iron content in a area of the Klondike, one is measured in, percent and the other one is measured in parts per million, I can compare them directly because their CVs will be both in percentage. I did a little example here comparing laptops to graphing calculators. Did a little study. I collected 20 laptops from my students and found that they weighed on average 6.5 pounds. The standard deviation of those values was 0.1 pounds. So the mean was 6.5, the standard deviation 0.1 pounds. Then I grabbed everybody's graphing calculator that they had to buy in high school but never get to use again, and I had 15 of those. Their average weight was 1 pound with a standard deviation of 0.1 pounds. Now, a layperson might go, well, they have the same standard deviation, so they have the same amount of variation. But like I said earlier, it's all relative to the mean. We can see that 0.1 relative to 1 is a lot more influential than 0.1 relative to 6.5. I did the calculations here. For the laptops, we get a CV of 1.54%, and for the calculators, we get a CV of 10%, indicating that the calculators are way more, there's a lot more variation in those calculators than in laptops, which you can tell I completely made up this example because that doesn't even make any sense. There's only like 2 or 3 calculator manufacturers, so I would expect them to all be relatively the same. where there's like 100 different laptop makers out there in different styles and such. So I would actually expect these results to be maybe reversed. So that's another thing we have to watch out for, is when we just make up numbers, sometimes we get results that aren't very good. But this is what we got stuck with today. So there we go. A couple more slides here before we end this video, talking about trying to understand standard deviation. That bell curve, we keep seeing it over and over again because that shape tends to occur naturally in so many situations where, most of the results are near the mean and not too many values are high above the mean or below the mean. You might think of this like, the heights of people. Everyone's around the same, middle type height, and then there aren't very many people that are super, super tall, and there aren't very many people that are super, super short, for example. So this shape occurs frequently, so frequently that we've developed this 68, 95, 99.7 rule that deals with the percentages of people or values in certain ranges of the mean. So if you have this beautiful bell curve and you start in the middle and you go one standard deviation above and one standard deviation below, like this range of values represents a certain percentage of the population. And you can see it's quite a significant portion of the whole curve there. It turns out to be 68% of that curve. To get that, we actually just, if we knew the equation for this curve, we could integrate that equation and find the area beneath the curve. Yeah, there is a little bit of real math in this course, I suppose. We will do some basic integration when we're talking about distributions like this. But in this case, I'm just giving this to you, the standard model. One standard deviation to the above and below the mean gives you 68% of your values. If you go out to 2 standard deviations, now you can see you have almost everything. You have 95% of all of the data. And so what's left in the little tails there, there's only 5% left. So if you're more than 2 standard deviations above or below the mean, you start to be in that unusual group of, 5% oddballs. If you go up to 3 standard deviations, this curve is just approaching, that's an asymptote there. So we don't quite get everything. We're at 99.7. This is important enough that I would say memorize this. However, I think our midterms will likely be open notes, open book. So me telling you to memorize that right now seems kind of pointless if that's going to be the case. I'll give you more information about the midterms as we go along. So don't hold me to that, especially if this is the year 2040 and I'm still using this same video. Maybe I'm doing something different with your midterms. I'm sure they're holograms and you have to arrive by flying car. Those percentages are nice to work with, especially, and they're easy to memorize, and we can use them in many situations because that curve appears frequently. Sometimes we don't have that curve. What happens if you have something that is skewed to the right, or what happens if you have something that's like this? Then those percentages go out the window. Those percentages only apply to that bell shape. But there's a smart guy named Chebyshev that came up with the percentages when you have alternate shapes. It's a fairly basic formula. He says that the fraction of a population occurring within k standard deviations of the mean is always at least 1 minus 1 over k squared. K has to be a value greater than 1, where K is number of standard deviations. That formula looks, a little confusing at first read. I thought I'd plug a couple numbers in, and then it hopefully will make sense. I plugged K equals 2 into Chebyshev's formula. Plugging K equals 2 means 2 standard deviations on either side of the mean. When you do that, you get 75%. So Chebyshev is saying at least 75% of my data will be within 2 standard deviations of the mean. In the picture that's drawn here, this area needs to be at least 75% of the total. It may be more. In fact, in this picture, it looks like it is more. So Chebyshev's theorem applies to these strange graphs, but it also applies to the bell curve as well, because at least 75% does include the number we memorized 5 minutes ago of 95%. The empirical rule said 95% of my values are within 2 standard deviations. Chebyshev says, well, it has to be at least 75. If you go out to 3 standard deviations, the empirical rule said it was 99.7, but Chebyshev says it's 89. He doesn't say it's exactly 89. He says it's at least 89. So Chebyshev's theorem is really nice because it applies to any distribution out there. But on the downside of it is that it's kind of vague by saying at least instead of saying a certain value. If we want the actual percentages, we'd have to figure out a model for these curves and actually calculate these areas beneath the curve. And in many instances, that involves having to do numerical methods to do the integration. You remember learning about Simpson's rule and trapezoid rule and all those things. Hopefully they aren't bringing back nightmares for you. But I won't, at least at this point, require that of you. I think that's a pretty good place to maybe consider ending this video. I think that's a good spot. We'll move on to measures of position in the next one. So hopefully you'll have a good day, and I'll see you at the next one.